So I'll be talking about public key cryptography here. So I think a lot of you must have heard of cryptography. It is ubiquitous in like whenever you use the internet or whenever you're communicating, it is extremely important. But it has been going on since I think around 4,000 years, since the Egyptians. So the main context is, this. The main context is you have two people, usually named Alice and Bob, who want to communicate over an insecure channel. So, in the ancient days, you can think of it as, two kings want to talk to each other, but their message could be intercepted, right? Or, in the context of internet, you could be sending someone a message, but someone could hack the channel and they could see your message. So we do not want that to happen. So the study of protocols and the analysis of protocols and even the breaking is called cryptography. So we'll assume, so the names we'll be using is Alice wants to send a message to Bob and Eve is eavesdropping. So before very recently, the cryptography was mostly based on private key encryption. So what that means is you have Alice and Bob, and before even communicating over the insecure channel, they already have a shared key between them. So something which is already known to both of them, but not known to anyone else. So usually how encryption goes here is, Alice has a message. She uses an encryption function which takes a key and a message and sends it to Bob. Right? So Bob receives some text called C, and to decrypt it, Bob simply uses a decryption function. So given a C, Bob uses a decryption function on it to retrieve back the message. Right. So this is just a definition of a protocol. Right. I haven't told you what the encryption or decryption function are, but I want this to satisfy some properties for this to be secure. So the first obvious property is that this should work correctly. That is, if they both have the same key, if I encrypt it and then decrypt it, Bob should get exactly the same message as what Alice sent. Okay, that is the most basic constraint we want to have. The second is, if Eve knows what is happening here, so Eve knows just this encrypted message, right? She should not be able to extract the message itself, right, without knowing the key. If Eve knows the key, then Eve has all the information that Bob has, and so nothing can be done there. But if Eve doesn't know the key, she should not be able to extract what M is. So, as an example, like many of you must have heard of Caesar cipher, which was used since very long. I'll try to encrypt one letter and using private key encryption. So I'm basically defining a private key encryption protocol. So let's say the key they settled on was 4. Written the example there. But so let's say the key they agreed on was 4, and Alice wanted to send one letter, which was N. Right. The encryption is just going to be to shift the letter Alice has by the amount given by the key. So, well, they both know the alphabet, let's assume. So if you add 4 to N, you get R. So Alice just sends R to Bob. Right. So this is the C which I mentioned before. Right. And what Bob can now do is, since Bob also knows what 4 is, Bob can simply say, you just go backwards in the alphabet by 4 letters and you'll retrieve back N. Okay? So you have shown that this is at least correct, this protocol which I have described. Now I also want to show that Eve cannot do anything even if she knows about R. So imagine from Eve's perspective, you just know that you just have the letter R. Now the key could have been any number from 0 to 25, right? So Alice could, like any letter, could have been encrypted to give R. So even let's say C, whatever the difference between the letters is, could have given R. So for example, like if the letter was P and the number was 2, that could also have given R. So Eve has absolutely no information of what Alice sent to Bob, right? So this is the idea of private key cryptography. But of course, this is a very simple cipher, and you can only use this to encrypt one letter, which is not very good. But there has been a lot of study since Shannon's time and so on, and we have gotten very efficient and very implementable crypto systems for private key encryption. But there is an issue here. The shared key is key to the whole protocol. So if Alice and Bob cannot meet beforehand to agree on the shared key privately, then you cannot do any of this, right? So why this is applicable is, well, firstly, you can't always meet on a secure channel. Let's say you're over the internet and you want to talk to someone really far away. You cannot meet them at a secure channel to just share the key and then talk after that. So this is the issue. And let us say even if there is a convenient way to share secret keys, you'll have to have a key for every person you're talking to. So you need to store keys for everyone you've messaged even once, or for every website you have gone to. So that is impractical to have. So so especially in systems like internet, this is not very useful by itself. So this is why in the 1970s, Whitfield, Diffie and Martin Hellman had the idea of public key encryption. So while what I'm describing to you might seem simple enough, or it's very doable, but at that time it was actually revolutionary. People could not think that this was possible. So the idea is as follows. So instead of sharing a key, so we are assuming they have not shared key at all. There's nothing shared between them. So there has been no communication between them so far. So what Bob does is, he generates two keys, a public key and a secret key. Right? Is this visible by the way? Okay. So as the name suggests, Bob can keep the public key anywhere. So Bob can just publish it on his website, or just whatever. Anyone can access, including Eve. So Eve can also access the public key. But the secret key must be kept to Bob himself. So let's say Bob generates these keys. I'll shorthand them to SK, PK, like secret key and public key, and post it on his website. So these keys are used when Alice wants to communicate to Bob. So when Bob is on the receiver's end. So what Alice can do is, given the message, encrypt it using the public key, right? And then what Bob does, so let's say this is C. What Bob does is decrypt it using the secret key, right? And we want this to be the message itself. So kind of nothing has changed. We are only using two keys which are there with Bob. Before there was just one key which was there with both of them. Now we are using two keys which are there with both of them, with just Bob.
Does Alice know the secret key?
No. The point is, no one other than Bob should know the secret key, right? Because there has been no communication, no secure communication yet. So, okay. So first question is, what can Eve even do at this point, right? So what Eve can do is, Eve can just encrypt, right? Because Eve just has access to the public key. Eve doesn't know about the secret key, so Eve cannot decrypt yet, right? The second thing is, okay, so what do we expect from the protocol? Firstly, correctness, right? If I encrypt something with the public key and decrypt it, it should be the message itself. And secondly, if Eve has access to the public key and this encrypted message, it should be in some sense hard to recover the message itself. So these are the constraints we want from a system, right? Yeah. So the point is that, like, one key property of the function should be that we cannot decrypt it without the secret key. Like, the secret key is essential to decrypting it. So yeah, so when we are talking about efficiency, what we'll need is that we need these two functions to be efficiently computable, because Alice and Bob have to compute it. But for Eve to decrypt, for Eve to figure out what M is from PK and the encryption message, it should be difficult. Is everything fine so far? Like any questions? Yeah.
Is from pk to sk, if you define a function, is that injective? Like,
From what?
if we have pk
Yeah.
and we want to know sk, will that be an injective function? Like for every pk is sk different. Otherwise, like we
Not
can have two different messages. Like
So what I'm defining is a protocol. So it is possible. So I'm just describing a pair. So it need not be different. But I'll make the decryption such that it will always give me the correct answer. So even if there are multiple SK possible, all of them will function so that it gives the correct answer. So that is up to the person who's designing these algorithms to, make sure it works correctly. So yeah. So what I'm saying is, if you have functions which work correctly, then what you're saying doesn't matter. It doesn't matter if it's injective or not. Does it make sense? Yeah. Any other questions? Yeah. So now I'll be moving on to actually constructing such a protocol, which is the RSA crypto system. Just some basic number theory you'll need is, I hope most of you are comfortable with modular arithmetic. And let phi of n be the Euler-Torschian function. If you don't know what that is or what that is, you just need two properties. Just the fact that if you have a number n and a number co-prime to it x, then I can raise x to the power of phi of n to get one modular. That is just the property of phi of n. And if you have product of two primes pq, then phi of pq is easily computable by knowing just p and q. P minus 1 times q minus 1. And the second thing we'll need is that if I can do the extended Euclidean algorithm on two natural numbers. So given E, which is let's say I'm given E and I'm given another M, and I want to find D such that ED is congruent to one model, right? Then I can use a Euclidean algorithm to find this D and F such that ED plus MF equals 1, and then that D will be the inverse modular. Right? You can ignore this if this is not clear because this is efficiency things. Yeah. So so I'm now describing the protocols. I'm describing a system which satisfies all the properties I want. So the first thing I need is to generate the keys, right? So this is something which Bob does initially before any communication. So what Bob does is picks two primes P and Q, which are extremely large. Like usually, even for day-to-day communication, we use primes around 10 to the 300. This is 2 to the 1024, but yeah, around 10 to the 300. So extremely huge primes. And compute n equals pq. I take the product. Since I know p and q, I can easily compute phi of n. It's given by that formula. And then I just choose any integer e, which is co-prime to phi of n. Right? So it will be 3, or usually the preferred value is something like 2 to the 16 plus 1. Just any number which is co-prime to phi of n. And then since I said it was efficient, I can compute its inverse. I can compute the inverse of E modulo phi of n. Right. So and the keys will be what will be known to the public is n comma e. So the e I chose in the beginning, and n, which is the product of two primes, and the secret key, which will be known to no one other than Bob, will be n comma d, where d is the inverse. Right? We don't want people to know the inverse. Does the protocol, is it clear what we are doing?
If you know E, you can compute D. Like if you know E and N, you can compute D.
That is the point. That is the what we say assumption that we can't do that. I'll come to that. Right? Because if you know NE, if what you're saying is true, then Eve can just find D, right? And then she has the key, and so this can't work, right? So the point is that you can't do this. But the key generation is fine, right? Like all the keys are generated. Yeah. So here is the encryption. It's simple. So if Alice has a message here, again, what Alice knows is just the public key, nothing else. So Alice knows N and E. So if Alice has m, then she computes m to the e, just raises it to the power of e, which she already knows, right? And what Bob does is, when he gets c, he raises to the power of e. Everything is mod n, that should be capital N, but I hope that's fine. Oh yeah, and also, like if you have a message, like a string, you can convert it into binary, which you can convert into number. So yeah, we can just do all of these things efficiently. So do people see why this should be correct at least? Why Bob gets the right message?
What should be the maximum size of
M. M should be less than n, because otherwise modular, like each residue, like each number less than n is fine. But if you go beyond it, you don't know whether it's 1 or like n plus 1. Like you can't differentiate, so you need it to be less than n.
So if like the message is bigger, you just make it into like n chunks.
Yeah, that you can do, but then the thing is, they're arguing for security is a bit muted here. But for now, I'll just assume that m is less than n.
Like
Again.
if you know m here, if
Yeah.
you know e here, like you can find out c, right?
If you know m and if you know e, c is just m to the e.
I mean, if can know, like if he knows the other informations, why can't he find out the message that like
Yeah. So basically, where the hardness. Okay, I'll come to that later. I'll come to why it's hard. But for now, I just want you to be convinced that it is correct at least. Right? Can people see that? Right. So, anyone wants to say why? Okay. So basically, what happens here is that so C is just equal to m to the e, right? So if we combine these two, say if I encrypt and then decrypt, I get m to the e whole to the d. Right? Yeah, exactly. So this m to the ed, and the way we define d, the way we define d versus that ed was component to 1.5. So by definition, this is ed is equal to some 1 plus k phi of n, where k is some integer, negative, positive, it's fine. But we know that m to the phi of n is 1. So this is m times m to the k phi of n, which is, okay, I guess I'll write it this way. This m. Is this fine? Okay, great. So at least Bob gets the correct answer. So now there's two things to check. First thing is that I should be able to do these operations efficiently, and Eve should not be able to do anything. Right? Again, I'll come to the hardness later. But first, okay, I think, okay, did everyone understand the protocol? If this, then I don't need to do the example. Is that right?
This part.
Yeah.
Like this part? Yes.
Yeah, correctness is fine. So here is the issue. I'm raising to the power of what, e and d, right? And that like all we know is that it's less than phi of n, which can be around 10 to the 300 if I'm choosing, or 10 to the 600 even. It's around pq. So I mean, if I just do the usual thing of, I'll just keep multiplying m one at a time. So m, and then I'll multiply by m, then I'll multiply by m, so on. That'll take me 10 to the power of 600 steps, which I do not want. Right? So turns out there is a fast way to implement this, and
It is DP.
dp kind of, yeah. So the point is that you can represent an exponent in binary, right, and just store like all the powers of 2 powers of n. So what I'll do is I'll just store a bunch of these values. So you can think of this as storing till like log e, many powers, right? This whole thing I can compute pretty fast because at each point I'm just squaring, right? So just as an example, if I had to compute, as I write here, m to the 2 to the 2048, I just start with m, square it again, right? Then it becomes m to the 2 square. If I square it again, it becomes 2 cube. So I just need to square it 2048 times, and I'll get this number. Everything is modulo m, by the way. Modulo m, let's say for now. Okay. So each individual power of 2, I can go to extremely large powers and compute it efficiently. Right. So what I do is I just pre-compute a lot of these values, log e many, and then I just multiply whatever is necessary to like get e, the value of e. So yeah, so as this example, okay, I wrote 2 cube and 2 to the 5, but this is 2 to the 50 and 2 to the 100. But yeah, so even if you have extremely large values of e, in log e many steps, you can actually, in around log e many steps, you can actually compute the power. Is that fine? Okay.
Given m could be a pretty big integer to begin with as well.
Yeah, so we are assuming that what we say, we
Wouldn't
can.
divide and conquer be far better, memory wise?
It'd be the same thing, I think.
No, memory will not be.
Oh, memory wise, yeah, that is true. Yeah, this is the simplest algorithm I wrote, but you can make it easy. Like you just do it one at a time. Right?
Like split in half. If it is odd, then.
Yeah. Yeah, I was thinking like you could just keep the current power of 2 in track and just multiply it if it's necessary, otherwise move on. Basically the same thing, but like in a loop instead of recursion. But yeah, so okay, so at least we can encrypt and decrypt efficiently, so that is fine. So now what we need to do is we need Eve to not recover m. Right? That was the concern you had. So I mean, I can't say more than we do not know this. We have not actually proven that Eve cannot recover m from m to the e. But what you said was that we can easily recover d from e, right?
No, like anyway, computing an inverse is hard. So
Yeah, exactly. Exactly. So that's it. Sorry.
too much computation power.
Yeah, exactly. So the point is that if you want to know ed equals, so the point is that you want to find this, right? But we do not know this. Given n, it's hard to compute phi of n unless you know the primes, right? So you can convince of this yourself, but if I have n equals pq, and if you don't know the primes, then to compute phi of n, even though it's just slightly, what we say, something like this, even though it's just slightly smaller, it's difficult to do this. And that is because we do not know of an efficient algorithm of factor, right? Let's say I found an efficient algorithm to factorize a large number, then I could just factorize, subtract the right names and have the answer. Right? Yeah, exactly. So, but the point is no one has found an efficient algorithm for factoring.
It's general question. If we have n and want to find phi n, what's the time complexity in that case? Respectively.
I do not know the exact, but I know that you can factorize in slightly less than exponential time. I'm not sure exactly how much. 2 to the root and something like that.
Another problem is what model of computation you are in. Because the normal model we use is called RAM, random access addition multiplication, in which division, multiplication, etc. are considered O of 1. In that, trivial U of n. But when we are actually dealing with big enough numbers, dividing and multiplying is pretty slow. So that is what we have to consider.
Yeah.
And a bunch of these things are open right now.
Yeah. So, sorry.
Like if n is small enough,
Wait, m is what? Okay, sure. Yeah. Yeah. So okay. Okay, I'll come back to this in the last slide as well. So what? Yeah. So the point is that if factoring was easy, then what you said is right. Okay, we can just quickly recover t. But no one has found an efficient problem, and if we are relying on RSA to be secure, we at least need factoring to be a hard problem, which we haven't proven. So we know, it is still possible that factoring is hard, but cracking RSA is easy, right? There's some other way from just knowing m to the e and the n and e. But what we can show is that if your path to decrypting is to compute the key directly, then that is equivalent to factoring. This is a nice algorithm which you could look up later. But again, this still doesn't prove much, because it is still possible that you decrypt this message without finding out the key. So we are just trusting that no one can solve factoring and no one can break RSA. So that's all for the talk. But so just a couple of comments. So we know that there are quantum algorithms to solve factoring efficiently. So in particular, if we have strong enough quantum computers, then all of the systems relying on RSA encryption will be broken. So which is why there is work being done on post-quantum cryptography, which is cryptographic systems which do not rely on RSA and factoring assumptions, and instead make other assumptions which are believed to be hard even for quantum. And then after this you might wonder why ever use private key. But all of this process does take a lot of time, and it is pretty inefficient when it compares to private key, especially for really long messages. So usually what people do is they just send a key through public key encryption and then just communicate privately. And for people who are interested in doing checking this out further, there is this website called cryptohack.org, which at least seems to have a lot of fun exercises in implementing cryptographic protocols and breaking them. And for people who are interested in more number theory side of things, there's a lot of interesting number theory and cryptography. That's it. I am not late.
What?
Yes. No, because last time I had Yes, any questions or just any you would ask me?
Thanks for the application of cryptography, like number theory and cryptography. Very hard that number theory is used but never solved.
Yeah, there's a lot more stuff. Like there's another public key protocol called Diffie-Hellman, which is another place where number theory is used. And again, all of these.
The rapid Miller probability test is like computes primes.
No, it given a number with high probability, it tells you whether it's prime or not.
It's not deterministic, right?
It's not deterministic, but it's really fast. The non-deterministic algorithms are really slow, so it's in practical terms.
Basically, what you do is finite basically, and there's some pseudo finite numbers which also pops up.
Yeah.
It is that test.
Yeah, so it makes sure that it avoids that problem with high probability.
Could you explain what this question is related? I didn't get the jargon.
Yeah, so he just said okay. For primes, there is this property that if you have this phi of n thing, right? If you have a prime number, then this is always true.
Yeah.
Right. So, the natural guess if you want to check if a number is prime, since I can do exponentiation easily, is just check for all numbers x whether this is true or not. So I'm given a number n, I'm going to check whether it's prime or not. I just go through all x, check whether this is true, and I'm hoping it's a prime. But it's possible, but it turns out there are numbers, composite numbers n, which satisfy this. Yeah. So Rabin-Miller extends that idea to avoid this issue, and it says with high probability whether a number is prime.
So how does that happen? Like when you explain the resolution, if that is possible or
I think the other talk should start now.
yes.
Yeah. But we could talk about it.
Sure.
Also, just an extension on this thing. The starting of the RSA, where we say we choose two primes.
Yeah.
The last primes were found using Rabin-Miller.
Yeah, exactly. So, before I said that just choose two primes, but you are looking at extremely large numbers. How do you even construct, like how do you just come up with a prime? So what we usually do is just generate a random number and check whether it's prime. And if you do this sufficiently many times by prime number theorem and stuff, you can show that you can find a prime reasonably quickly. Is the point with that problem. So yeah. So I mean, now that Alice and Bob can communicate, we'll see what they can do together. Yeah.
Hello guys. So now Alice and Bob know how to communicate. How many of you have siblings? Have you? Oh, okay. And how many of you have struggled with a slice of cake? You have a last slice of cake and you are having it good. Ek bar. So now imagine we are in an alternate universe where the siblings are a bit civilized. They have money. First of all, they have money. They have enough pocket money, and they're gonna bid to see who gets this last slice of cake. Okay, this is the motivation behind winning games. Yeah, so it's winning games. So first I'll introduce games played on graphs. Is everybody familiar with directed graphs? Or also, in between, if you don't know some notation, please ask me. Right, everybody's familiar with directed graphs. You have a directed graph, V is a set of nodes and E is a set of edges, directed edges. And you have two players, Adam and Eve, or in his case, Alice and Bob. And you have a token. We'll replace that, we'll see that by a slice of cake. And this is placed on some vertex. So you have a graph, and on some vertex, you have a cake on it. Each player has some budget, money, and in each turn, we hold an auction, bidding to determine which player moves the token. Simple enough. We are bidding to see who gets to move the cake. Right. Let's look at an example. The cake is kept here, and Adam has 10 tokens of money, say. Eve has 20. Both of them bid simultaneously. So imagine, this is where I'll use this. Both of them want to communicate and they want to send the bid simultaneously to a third person. Both of them bid simultaneously. Say Adam bids 5 and Eve bids 6. They don't know what the other person are bidding. Say they bid it to a third person. Now, since Eve bids more than Adam, Eve gets to move the token. So Eve chooses vertex 2 and moves the token there. But Adam gets 6 tokens extra and Eve loses 6 to keep the game fair. Eve gets to move the token, but she also loses the bid. She also loses the money to the other bid. Is that fine? Now, Adam's budget is 16 and Eve is 14. Both of them bid simultaneously. Now, notice that Eve has less than Adam. So Adam can go all in and Eve cannot prevent that. So Eve also goes all in. Eve goes 14, Adam goes 15, Adam wins. Adam chooses vertex 4. And at this point you can see the game is finished because there is no outgoing edge. So we'll see who wins, and not right now is not determined, not said what determines the winning game. But yeah, now the game is finished over here. Formal definition, this is fine. Bidding scheme. Eve's budget is capital B Eve, and Eve's bid will denoted by small b Eve. Adam's budget B Adam, and Adam's bid is B small b Adam. And if B Eve is greater than B Adam, this is the change in their budgets. Continuous bidding. So now imagine that you have money, but it can be a decimal as well. It's not discrete. You don't have coins anymore, but you can bid any decimal. So their total budget is 1, and they can bid any decimal between 0 and their budget. Now we have established how the game works, but we haven't talked about who wins the game. On what conditions can we say, oh, Adam has won the game or Eve has won the game? That is what we call winning objective. When does a player win? And we are not assuming ties and all. We'll say if Adam wins, if and only Eve loses, and Eve loses if and only Adam wins. So there are multiple winning objectives: reachability, bushy, parity, mean, payoff. I won't define these three, but we'll look at reachability. Reachability, as the name suggests, if you can reach a vertex. Adam wins if Adam can reach a vertex. Eve wins if Eve can win a vertex. Or if Eve wins a set of vertices. If she reaches any of these vertices in T Eve, she wins. And Adam wins if the token reaches T Adam. Game stops after either T Eve or T Adam is reached. Threshold ratios. Yeah. So as I said, we want the games to be complementary of each other. So we either want Adam to win or we either want Eve to win. And what we'll see in this talk is it is actually determined. Given if we can know how much money Adam has and how much money Eve has, and on which token on which vertex the token is kept, we can determine who will win. Assume that both of them are very smart, they have infinite intelligence, and nobody one of them is going to make blunders, I think. So we can tell who will win. Basically, we can give a winning strategy that no matter how the other player plays, given this is the state, this is the configuration, I will always win. And if I don't have this, then it means the other player will always win. We'll clarify then this as we go along.
I have a question.
Yeah.
So at no point are we considering any value for the cake, like what Adam's values it at, or what values it at?
No. You mean value of the cake?
Yeah, it's not like the cake is the main goal. Like
Yeah, it's the main goal.
highest.
Yeah, highest.
Okay.
It's 1. Let's say. Value is 1. Is that fine?
Yeah.
What is the necessary and sufficient initial budget ratio that guarantees winning the game? So, example. This is a graph, and initially the token is kept here. Let's say Adam wants to reach T2 and Eve wants to reach here. So if the initial configuration is this, that is the token is kept at B0, Eve has 0.75 plus some small amount and Adam has 0.25 minus some small amount. I won't do this because I want you guys to have lunch on time. Yeah, you can maybe take a screenshot of this, I'll put it on later. You can do these as exercises. It is enough for Eve to win. Whenever Eve has this much, Eve has a strategy that no matter how Adam will play, Eve can say, I can always win. But it is not necessary. By that I mean, even if Eve has less than this, say 2 by 3rd plus epsilon, she can win and it is sufficient. As in, if Eve has 2 by 3 minus some epsilon, she will lose. That is what we mean by sufficient. This is the minimum amount of money she needs to win. And if she does not, it's not that the game will go to a tie. It means Adam will definitely win. Adam will have a winning strategy. So,
could you explain the question and I just show how the game would work? Would it be multiple cycles between V0 and V1 before anything moves on?
kind of, yeah. So there will be cycles here and then...
because the plus epsilon keeps on piling up till it eventually becomes greater
Exactly.
than that she can make it.
Exactly. Exactly. So epsilon keeps on piling up and then Eve has enough money that she can just force the game to T1 in 2 steps. That's the idea.
And how many steps?
Oh no, after she has piled
Ah.
up here. I mean, I don't remember. I think she can pile up enough money in V1 also. So in 1 step she can just force the game to T1.
How that would I bet 1 upon 3 minus epsilon.
Here?
She bets 1 upon 3 plus epsilon. She ends up with 1 upon 3. I end up with 1 upon 3. It's a tight condition.
You're talking about this.
Here's the second case. What happens with the tight condition?
We'll look at it later.
Okay.
Yeah, we'll discuss it after that. Formal definitions of threshold ratio. So B Eve is in 0 to 1 initial budget, and we'll consider a function threshold. Threshold TH is a function from the vertices to 0, 1. And threshold ratio of a vertex B is such that if Eve has more than this threshold, Eve can win the game from that vertex. It's specific to that vertex. And if she has less than the threshold, Adam will win. And when Eve has exactly equal to threshold, it's a bit tricky and messy. It depends on the tie-breaking mechanism. So we won't be seeing that. We'll only see when it's threshold plus epsilon. Yeah, so now we look at reachability continuous bidding game. Continuous bidding games, you can bid a decimal, and reachability is the objective. Now, played on a directed acyclic graphs. Do you know what directed acyclic graphs are? Just a directed graph which has no cycle. So we look at two theorems. First is, okay, what I want to say is, you can, if I can say for each, you are given a general graph, and for each vertex I can give you a threshold function. I can give a threshold function for an entire graph. This means that the game is determined, right? Just by looking at the initial vertex and the budget ratio, I can tell you who wins the game. So if I prove that threshold budget exists in an arbitrary graph, we are done. We can say the game is determined. To do that, first we look at tax. Also, I won't be doing theorem 2 for general graphs because I won't be having the time. But the slides are available. I can share the slides. It has a proof for theorem 2. We'll only look at threshold at theorem 1, which says it exists in every game played on an app. Yeah. So our goal is to define a threshold function and to prove that it acts like a threshold function. How can we prove it? By giving a winning strategy. Correct? First, we'll define a function t, and we'll later prove this t acts like a threshold function. T function from v to 0, 1, we will prove this t coincides with threshold function for e. So we'll do this by induction. Since it's a DAG, you can visualize, we can sort of do easily, right? We can start at the sinks, then we can go one layer up, and then all the way up to the roots. Base case, S is a sink. Oh right, sorry, I think I missed one thing. Yeah, so set of sinks, we have a set, and we have target set for Eve. Target is a set of sinks, or is a subset of sinks. So the target set for atoms is a sink which is not in TRG. Okay, so this reachability is whenever you reach a sink. If that sink is good for Eve, Eve wins. If not, atom wins. A target vertex is not a vertex in between, since we want the game to terminate as well. Yeah, we'll define. Now S is a sink. We define TS to be 0 when S is in target. Does that make sense? When you are at a target vertex, Eve does not need any money because she has already won. So it's 0. And if not, then it's 1. Because the game terminates when you reach a sink, and since that sink is not a target vertex, it's not a good vertex for Eve, she cannot do anything. Even if she has all the money in the world, she cannot win. At this point, we can see that T is behaving like a threshold function, TH for the sink. So you all agree? Yeah. Eve requires no budget to win from a target vertex, and Eve cannot win even if she has all the budget. Inductive step. Consider a vertex V such that T is defined for all its children. Since we can go bottom up, so assume that for all of its children U, we have proved that this TU acts as a threshold function. We proved this for the sinks, so our induction base case is clear. Now we are doing the inductive step for all its children. Threshold is defined. Let V plus and V minus be the two children of V that respectively achieve the maximum and minimum values of T. So I have a vertex. Does that make sense? I have a vertex. I have all my children. Look at the vertex which has a maximum value of T. I call that V plus, and which has a minimum value of T. I call that V minus. So right now it should, like, just think about it. If I want to play smartly, I have some money. I would like to go to a V minus vertex, right? Like, I would like to save my money. So this is exactly what we'll do. In case of multiple children, choose arbitrary, that doesn't matter. And we have T of V, TH of V plus defined and TH of V minus defined. We'll now define TV is half of TV minus plus half plus TV plus. And we are defining this. We'll define this for all the graph. And then we'll prove that it acts like a threshold function by giving how Eve can win. Yeah.
Could you help me get for TV minus TV plus R?
So, do you understand what V plus and V minus are?
Sorry.
Yeah. So, I'm at a vertex V.
Okay, got it.
Yeah, it's the maximum, it's a child with the maximum value of T.
Okay, yeah.
And V minus is a child with minimum value of T. Now we'll prove that this acts like a threshold function. Suppose at a vertex V, Eve's budget is TV plus epsilon. So if we have to prove, our definition is it acts like a threshold function. If Eve has a little bit more than threshold, she has a winning strategy. So assume she has a little bit more than threshold, or sorry, a little bit more than TV. We will describe a winning strategy. Her bid would be half TV plus minus TV minus. We'll see how the math works out. If she wins, she moves the token to V minus because she wants to save the money. We'll say her action is V minus B Eve, as in she wants to go to the vertex V minus by bidding this much. We don't know about Adam's action because we are building a strategy for irrespective of how Adam is playing. So let Adam's action be U, like Adam has chosen the vertex U and B Adam. There are two cases. Eve wins the bid and Adam wins the bid. When Eve wins the bid, Eve loses B Eve amount of money. So TV minus B Eve is exactly TV minus. So I'll just write this quickly now. TV is half you subtract this, you get half 2 times T V minus, which is T V minus, but since she had a little bit more plus epsilon, so it's her final budget would be T V minus plus epsilon, and by induction we know that this is fine. This is winning for Eve by induction hypothesis. Now if Adam wins the bid, we have so T V plus B Eve is T V plus. Do you see how? This is T Eve and oh yeah, if we just have to plus it, this will be this, so it will be T V plus. So if Adam wins the bid, we know Eve gets the money, right? But we don't know how much Adam has bid, but we know it is at least B Eve. B Adam is at least B Eve. So she will have at least T V plus. Does that make sense?
Since it is the maximum of the children she can.
Yeah, it's a maximum of the children, yeah. So, so at U, she has at least TV plus epsilon, and which is greater than TU because by definition TV plus is maximum among all its children. So we know even if she loses the bid, and no matter what vertex.
What was U again, by the way?
U is the child. U is the vertex that Adam picked.
I see.
Yeah, while bidding. So while bidding, you pick a vertex that if you win the bid, you would like to go to this vertex. Yeah. So even if she loses the bid, and no matter what child Adam picks, Eve will have enough money to win there. Since she had enough money in the beginning, since she had enough money at V to win, so if she wins the bid, she'll have enough money. Even if she loses the bid, that doesn't matter. She will again have enough money to win. So we can see that in the beginning, if she has enough money, then at second step she'll have money, and so on, and it will go to the sinks. Therefore, she will have enough money, and then she'll go to the target vertex. Yeah, so we showed that this acts like a threshold function for E. That is, if she has THV plus epsilon, E will win. Now we need to show if she does not, it means she has THV minus epsilon. So we flip the game. We just define t prime v to be 1 minus tv. And at the sinks it flips, because if it's a target sink, then Adam cannot win. If it's not, then Adam can win. Which matches that Adam wins at sinks which are not target. So we can do all those induction steps that we did for Eve. It's absolutely symmetric. And we can see if it's not a sink. So t prime v is 1 minus tv, which simplifies to this. So it is exactly matching the behavior that we had for t. T prime is mimicking the behavior of t, which shows that, yeah, since this is just some math, b Eve plus b Adam is 1. So if b Eve has less than threshold, it means b Adam has more than his respective threshold. Adam can apply the winning strategy to force the game to S target, S minus target. That completes the proof. Is everybody convinced that this game is determined?
But Adam has more than t prime. How does that apply that?
Sorry. If Adam has more than t prime v, how does that determine that? So I skipped that part. I said that t prime v behaves exactly like yeah, so we can prove all of that for t prime v. So after we have proved that, then we can say that it acts like a threshold, and yeah. So the game is determined since we have the threshold for Adam and Eve. Then this is the theorem for normal graph, which I won't be doing. So if you want, I can share the slide.